Hi friends, welcome to lecture 82 on our helicopter dynamics course, and today we continue with ground resonance. Specifically, I'm going to discuss about hub motion and lag coupled equations. So in the previous lecture we derived the equations for lag, converted them to fixed frame, and now we are going to include hub motion into these equations. So let's take a look at the typical rotor blade, and here the blade has lag motion here. So if you only had lag motion, you would have this r zeta double dot term as the forcing term or the acceleration term. Now because of the hub motion, you also have xh and yh coordinates, and corresponding to these two directions you also have xh double dot and yh double dot. And now when I look at this particular point, I get the acceleration here. So let's take a look at how we get it. The r zeta double dot term is of course coming purely from the lag direction. So there is a lag motion here, and r is the length from the root of the blade to the point at which you are at. So at this section. So that's the source of r zeta double dot. Now you look at xh double dot. So xh double dot is in this direction. So if I take the component in this direction, which is parallel to r zeta double dot, I will get xh double dot into sine psi. So this angle being psi here. So that's this component here. And I will get negative yh double dot into cosine psi. So that's the component in this direction. So that essentially is the acceleration which acts at a given point at a distance r from the root. So now we can write the coupled equation involving lag and hub motion. So remember from our previous lecture, for the lag equation we have our usual zeta double star term, we have the stiffness term, we have the damping term, and now the presence of hub motion has given us these two new terms here. And again, remember, I zeta is the second moment with respect to mass, and S zeta is the first moment with respect to mass. So I zeta comes here in front of the blade part, and S zeta comes here in front of the hub motion part. So what we are going to do is we are going to develop a 4 degree of freedom model for ground resonance. And so we have the rotor here and we have the body. Now we are going to assume the body can be represented by 2 degrees of freedom. These are going to be xh and yh. And also corresponding to this body, there are going to be stiffnesses and damping. So kx, ky are the two stiffness components, and Cx and Cy are the two damping components, and the rotor is held here with these particular body motions and body stiffness and damping components. Now the question is, which of the blade modes should we include? The blade modes are now in the fixed frame. So we saw in our previous lecture that for a 4-bladed rotor there was no shift of rotor CG when collective lag zeta 0 or differential lag zeta 2 was used. The important lag motions are the zeta 1c and the zeta 1s, which cause lateral and longitudinal shift of rotor CG. So these were the ones which were having an impact on the rotor CG, and therefore these are the motions which are going to couple with the in-plane, longitudinal and lateral hub motions x, h and yh. Therefore from this physical knowledge which we have, we can presume that a 4 DOF model is useful for ground resonance, and this 4 DOF model includes zeta 1c, zeta 1s. These are the lag degrees of freedom in the fixed system, and xh and yh, these are the hub motions. So if we now take the equation we discussed some time before and we transform it to the fixed frame, we get these two equations here corresponding to zeta 1c and zeta 1s. And as you can see here, there are the usual terms which we obtain when we transform the blade equations, and then there are these new terms which we have obtained depending on xh and yh, which are there due to hub motion. And again, I zeta is the second moment and S zeta is the first moment with respect to mass. So these can be calculated if we know the mass per unit length of this particular blade. So now what we are going to do is we are going to try to estimate some of these values, and we'll do that soon. So let's look at some of these nomenclature. So for example, C zeta star is the damping coefficient in the rotating frame due to lag damping. Now, the nature of mechanical damping from lag as well as support damping is generally quite nonlinear, but what's done is that for mathematical convenience, these damping are calculated by equaling the energies dissipated in one cycle of motion. So essentially, equivalent damping concept is used to come up with a suitable viscous damping which can be used in this model. Now let's look at the hub. So as far as the hub motion is concerned, we assume that mx and my are effective masses of the body hanging in springs in the x and y direction respectively. And the rotor forces excite the body, therefore the equation of motion for the body can be written like this. So we have mx xh double dot plus kx xh plus cx xh dot is h. So h is the rotor force in the xh direction. And similarly, we have the second equation here in terms of YH, and again Y is the rotor force in the Y direction. So these two equations are important, and we are going to now look more closely at some of the remaining terms here, which are H and Y. Now, to calculate H and Y, we have to figure out what are the forces which are acting at the blade section. So let's take a blade section here. And what we do is that we try to figure out what is the SR and SX force which is acting at this section. So let's look at SR first. So of course SR is going to have one component purely from the lag motion. You remember the lag Coriolis component. But then there are also going to be components because XH double dot and YH double dots have component in this direction. So let's take a look at, for example, XH double dot. So XH double dot into cos psi would be component in this direction. And so this gives us this component here, XH double dot negative into cos psi. Then YH double dot here, that's going to have a component in this direction, and that's also going to be YH double dot sin psi. So that's the component like this. Now if we look at Sx, now here the zeta double dot component is there, which is acting in this direction here. So that component is here. Now there is also a component here due to centrifugal force type of situation. Now let us look at the xh double dot. So xh double dot is now going to have a component which is in the sinusoidal direction. So that's the component here in this direction. And then YH double dot has a component which is in the cos direction. So essentially these are the X component and R component of the S force, which is the local force here. And then we are going to sum this across all the rotor blades to get the H and Y forces. So the H and Y are the hub forces, and to obtain these forces we essentially use the Sx and Sr values and perform this summation from m is 1 to n. And if we do that, we get these equation here. So these two equations. Now you can clearly see one part of this involves zeta, and this comes from the zeta part of those forces which we saw in the previous slide. And the second part involves xh double dot and yh double dot, and that comes from the forces which were related to the motion. So once we get these two, we are then in a good position to write the equations. So before doing that, some more nomenclature. You of course remember N is the number of blades, and now MB is the blade mass, and also CX and CY are the damping coefficients of the supporting structure. So that's the body equation now. We got the H and Y forces, you remember that, and then we are able to move those components to the left hand side. So remember, one of the forces was NMB related, so that comes here, and the second force was zeta double dot related, so that comes here. So this essentially gives us the body equation, and again there is coupling between the body motions and the lag motion in the fixed system. Now, if there is no coupling term present, then the frequencies of the support would be given by these two equations here. So let's define Cx star in this manner, Cy star in this manner. All these definitions are just going to simplify our equation, and then we can write this 4DOF lag body equation system in this form. So here you have a mass matrix, you have the degrees of freedom here, the acceleration terms, you have a damping matrix, you have the velocity terms here, you have a stiffness matrix, you have the displacement terms here. So you clearly now see that our 4 degrees of freedom were zeta 1c, zeta 1x, s, xh, and yh, and these degrees of freedom are now present here. Of course, we see the damping matrix, we have all the diagonal terms here, and then we have the Coriolis term here, the negative 2 term, and here also we can see some of those type of terms present. Now, this equation is going to become very important, as we will see later, and of course this equation currently sums to 0 because we have not considered any aerodynamic force as such. Remember, ground resonance is a mechanical instability. So some of these constants actually simplify if we assume uniform blade. So if we assume uniform blade, as zeta star becomes 3 by 2, mx star becomes this value here, my star becomes this value here. So again, remember that some of these mx and my were related to the support masses, and the mb was the mass of the blade, the n is the number of blades. So NMB is the total rotor mass, because MB is the mass of each blade. If I multiply that by number of blades, I get total rotor mass. So for uniform blades, the two terms which are present in that mass matrix, S zeta star by mx star and S zeta star by my star, essentially become half, and these are like rotor mass by support mass. So again, for uniform blade, all these terms become substantially simple. So in general, the support mass is much larger than the rotor mass. These equations which we have obtained are of course of size 4, and they are ODEs. So essentially there are 4 equations, and these are differential equations, ordinary differential equations. And the stability of this system can be estimated through determinant calculations and analysis, and by looking at the eigenvalues of the matrix which is obtained. And that we will do in our next lecture. So I will see you in the next lecture, where we will discuss further about ground resonance. The main thing today was to understand that ground resonance happens because of the coupling between the lag motion in the fixed system and the hub motion. So again, this is a clear case where FCT is required, because we need to transform the equations of the lag motion from the rotating system to the fixed system. And once we do that, the simplest model we can have is the 4DOF model, and with that we can predict some of the ground resonance phenomena. Now, of course, if you wanted, you can have more degrees of freedom also, and there are of course models where more degrees of freedom are used, but this is the simplest model you can have, through which you can capture the physics of the problem. And again, through the principle of scientific parsimony, we always want to keep the simplest model which we can do with in any physical situation or in any engineering situation. So I'll stop here, and I will see you in my next video. See you then.